said, hey, you, let's do some DiffEQ. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some DiffEQ. Today we're going to talk about higher order characteristic polynomials. That means we'll be looking at differential equations that are linear, homogeneous, and constant coefficient. In such cases, we're able to find a characteristic polynomial and use that to find a general solution to that differential equation. Let's go ahead and talk about superposition, which is a concept we saw with second order linear constant coefficient differential equation. The principle of superposition says that if you have a linear, homogeneous differential equation, it doesn't even have to necessarily have constant coefficients. As we see here, they can be general functions of x. But if it's at least linear and it's at least homogeneous, and you're able to find n linearly independent solutions, then it's true that their linear combination is also a solution. Now, the reason for this theorem is that when we have a differential equation of, let's say, nth order, we're going to be looking for n linearly independent solutions. And it follows from this theorem that this linear combination is also a solution. In fact, it is, in some sense, the fullest general solution. We'll get these n linearly independent solutions from the characteristic polynomial. Now, as it was mentioned, we're going to be looking at differential equations that are linear, they're constant coefficient, and they're homogeneous. The previous theorem didn't require that the coefficients were all constant, but in order to come up with a characteristic polynomial, they certainly have to be. So the constant coefficient is what allows us to have a characteristic polynomial in addition to linear and homogeneous. Now, if your linear, homogeneous, constant coefficient differential equation looks like this, then we get a polynomial that you'll notice is very similar, where the nth order term in the equation, the differential equation, down here is matched up with the r to the n term. The coefficient is exactly the same, and it's a constant, so a sub n is some constant number. We see with the n minus first derivative, we have r to the n minus 1. And again, the coefficient is exactly the same. And so on and so forth. The first derivative corresponds to r to the first. The zeroth derivative, which is just y, corresponds to r to the 0, which we can just omit because it's just 1. And this is our polynomial here. Since we're going to be looking at a polynomial, then looking at the roots, in order to tell us what the solution to the differential equation is, we really want to recall what the fundamental theorem of algebra is. It simply says that if you have a polynomial equation of degree n greater than or equal to 1, and the coefficients of this polynomial are real, which they will be for the types of differential equations we'll look at, then that polynomial equation has n complex roots. And it's important to stress here that it's n complex roots, that we have up to multiplicity. That is, there can be some repetition of roots. The fundamental theorem of algebra actually says we could have complex coefficients in general, but let's state it in terms of having real coefficients for us, since those are the types of polynomials that we'll be looking at. But it is going to be the case that sometimes we'll have complex roots, and there's no avoiding that. Now, here's an example of a fourth degree polynomial. That means, according to this theorem here, if there's n degree, fourth degree, it should have n complex roots, up to multiplicity. Now, the roots are going to be x is equal to -4 and x is equal to 3. Those are two roots that are real. Now, a real number is a complex number. So when we say complex roots here, we mean complex in the general sense. Some of them can just be real, but a real number is also a complex number. but not all complex numbers are real. Besides the real roots, there's also a pair of complex roots, and these are complex conjugates. A pair of complex conjugates are simply the same complex number, with the exception that the sign in front of the imaginary term, the one that has the I, that's going to be different between the two. If that's the only thing that's different between the two, we call them a pair of complex conjugates. And another important thing to notice or to note is if one complex number is a root, then its complex conjugate is also a root. So these will always come in pairs. That's certainly worth noting. And now we see with two real and a complex pair, that gives us a total of 4 roots. And that corresponds to the 4th degree here. Now, depending on what types of roots you have, you'll end up with different terms in your solution to the differential equation. But first, let's note that there are important properties of the roots which completely tell us what the terms in the general solution should be. The first property is whether you are looking at a real root or a complex pair. And again, when you have one complex number, you always have its complex conjugate. So complex numbers always come in pairs like that. One's a root, its complex conjugate's also a root. Besides knowing whether it's real or it's complex, you also have the number of times that it appears, which we call its multiplicity, or in a more colloquial sense, its repetition. If we have, let's say, x squared minus 1, that has 2 roots. One root is x is equal to 1. Another root is x is equal to -1. Both of these are real. Both of them appear only one time. In the second polynomial here, there are 4 roots. The root of x is equal to 2 appears actually twice, 2 times. It's a real root, but it has multiplicity 2 since it appears twice. Now, what does that mean? Well, you could rewrite this polynomial as x minus 2 times x minus 2 times some x squared plus ax plus b. I'm not actually sure offhand what a and b are, but it's not exactly important at this moment. The important thing is that if we look at this factoring of the polynomial, we see that 2 is a root, and it's a root twice because x minus 2 appears 2 times. So this is where we have the multiplicity 2. And then it's from this part that we get 1 minus 3i and 1 plus 3i. Now we'll say that complex conjugate pair has multiplicity 1. The pair only appears one time. But again, remember, if a complex number appears, so does its conjugate when we're talking about them as roots. Looking at another example, we have this polynomial, and if you factor it, like we've shown here, what will happen is that you have one factor that's x minus 2 minus 3i, and then you have that same thing again. And of course, if we have x minus 2 minus 3i, we have x minus 2 plus 3i, because 2 minus 3i and 2 plus 3i are complex conjugate pairs. So we have the pair appearing once here and then a second time here. Therefore, the complex conjugate pair has multiplicity 2. So we've talked about here the important things to keep in mind for roots are whether they're real or complex. And if they're complex, they're always going to come in a pair. And how often either the complex pair is repeated or the real root is repeated. Or said another way, what's its multiplicity? Now, in order to find these roots, I've just stated them here, but what you'll need to do is actually be able to find the roots once you have the characteristic polynomial. The way to do that is through polynomial long division. So suppose we have this characteristic polynomial here, and we want to ask ourselves, is 0 a root? If you check that 0 is a root, you substitute it in for r, for instance, you'll get out -4 that's not equal to 0. That means that 0 is not a root. Do the same thing for -1. Is -1 a root? Substitute it in to the polynomial. R is equal to -1, you get -10. That's not 0, therefore it is not a root. Finally, substitute 1 into this polynomial, and you'll find that you do get 0. That means that 1 is a root. Once you have a root, that's where you'll use polynomial long division. So we factor this polynomial using polynomial long division, and that helps us find the other roots. Let's say I want to divide the polynomial r minus 1, and I chose r minus 1 because 1 is a root. Say we take that and divide it into this polynomial. Here's how it works. We repeat this algorithm over and over. So here's the algorithm. So the first thing is to multiply in order to match terms. Now what we mean by that is we take this r and we see what we need to multiply by to get to this r cubed. Well, r times r squared gives us r cubed. So we say r squared. Picked r squared because that's what we had to multiply this r by to get to r cubed. Now that we have that, we're going to multiply back through. In order to multiply back, we take this r squared and we multiply it by all of this. That will give us r cubed because, as expected, r squared times r is equal to r cubed. And then we have r squared minus 1. So then we have minus r squared, where here we subtract r cubed minus r squared plus 4r minus 4. We subtract from that this here. If you do, I think you'll get 0 because r cubed minus r cubed. And then we have negative r squared minus a negative r squared plus r squared. So we get plus 0. But we also then get that these terms migrate down. And now we start the whole process over again, where we multiply to try to match terms, where now we're going to multiply this r times something to get to 4r, which is obviously 4. We'll multiply the 4 back through, giving us 4r minus 4, subtract, and that'll leave us with nothing. So remainder 0, which if you have a root, you're always going to get remainder 0. So if you don't get remainder 0, something went wrong. So what this shows is that this polynomial is equal to r minus 1, that's this here, r minus 1, times r squared plus 4. Using the fact that we knew 1 was a root, we factored out r minus 1, leaving us with r squared plus 4 from polynomial long division. And now it's easy enough to find the roots of this, which is going to be plus and minus 2i. Now let's look at some examples where we put all this together, starting with a differential equation, to actually find a solution. Here we have a third order differential equation. It is linear, it's homogeneous, and it's constant coefficient. That means there's a characteristic polynomial, which is, and what we can do is test some roots to find that one of the roots is -1. And from this, polynomial long division shows us that it factors, like so. And then r squared minus 4 obviously factors like so. Now this gives us 3 distinct real roots. R is equal to -1, r is equal to -2, and r is equal to 2. Now from this, we get solution terms that will be a part of our general solution. Each one of them, in the case of a non-repeated real root, is simply going to be e to something. y1 will be e to something times the independent variable x. y2 will be e to something times the independent variable x. And y3 will be e to something times the independent variable x. Now the somethings are simply just the roots. So -1 times x, -2 times x, and 2 times x. Then by superposition, since these are linearly independent, we now get a general solution that's just the linear combination of these. Now as usual, if we check for singular solutions, we're checking for some y sub s is equal to k. Taking the derivative of k will give 0, and substituting that into the differential equation will give us that -4 times k is equal to 0. That is, we take k and we substitute it in here, where the first derivative of y, if y is a constant, is just 0. So is the second, third derivative. So we just get -4y, or in this case, -4k. And that shows that k must be equal. And now notice you can actually recover that from this solution formula. The reason you can recover it is because it's possible for C1, C2, C3 to all be equal to, and in that case, you just recover y is equal to 0. Let's look at another example. Here we have a third order differential equation again. This is characteristic polynomial. If we check for the roots, we'll find that p of -1 is equal to 0. That means -1 is a root. Now, doing the polynomial long division, we'll take r plus 1, which is r minus -1. We'll divide that into the polynomial r cubed minus r squared minus 5r minus 3. Following the algorithm, we'll end up with, now this gives us a factorization that p of r is equal to r plus 1 times r squared minus 2r plus 3. Now, once you have a quadratic like we have here, you can find the roots of this simply using the quadratic formula. Using polynomial long division, we get the following factorization, that p of r is equal to r plus 1 from the root of -1. It's r minus -1. And then r squared minus 2r minus 3. Now, once you have a quadratic that is a degree 2 polynomial, you can use the quadratic formula. That will give us two more roots. One of those roots is going to be equal to 1 plus 2. The other is equal to 1 minus 2. Remove this work here. This gives us three roots. The first root we found to be -1. Another root we found to be -1 from the quadratic formula. And then finally, a third root is going to be 3. Now, we would align this very similar to the last problem, where over here we have e to the -x, because we had -1 as a root. Then here we would have e to the 3x. Now, there's an exception here. Because we have a multiplicity of 2 with the -1 root, we won't just have e to the -x twice, and we won't just have it once. What we will have is e to the -x multiplied by a polynomial. The polynomial that we multiply will depend on how many times the root is repeated. It's repeated 2 times, so we'll have a polynomial that has 2 terms. That would mean we have c1 plus c2x. Starting with a constant of c1, we then keep scaling up the polynomial to a degree such that we have a number of terms equal to the multiplicity. The multiplicity is 2. 2 times this appears, so we have 2 terms in this polynomial. Now, if we take the solution formula, we have y is equal to c1 plus c2x times e to the -x plus c3 e to the 3x. Now, we could have put a c3 back here, or we can wait till we actually assemble it into the whole solution formula. It doesn't matter. We will want to, though, when we multiply by the polynomial, keep track of the different c's. Again, there's going to be a singular solution in this particular case. There'll just be one, and that singular solution is y is equal to 0. Let's look at our next example. The characteristic polynomial of this differential equation will be, one can check that this factors in the following way. And that means we have a repeated real root, 3 times repeated, or multiplicity 3. If we were to just have one of these, we would have a solution term of e to the -x. Now, since it's multiplicity 3, we're going to multiply by a polynomial, and the number of terms that polynomial should have is equal to the multiplicity. It's multiplicity 3, so there should be 3 terms, namely a c1 plus c2, and now x. All these terms should be linearly independent, and then c3x squared. That's all of the roots, so this is actually our solution formula. And like usual, there's a singular solution of y is equal to 0. We'll look at 2 more examples. Let's do the second to last. So here is a differential equation that is not linear. Just kidding, it is linear. Of course it is. But it's not constant coefficient. Just kidding, it is constant coefficient. But it's not homogeneous. Just kidding, it is. And I'm sorry, but recording these videos alone for long periods of time, all day long, several days in a row, starting to wear on my sanity. I need something to amuse me. This is, of course, a linear, third order, constant coefficient differential equation. That means we can find a characteristic polynomial. That characteristic polynomial is going to be checking that p of 1 is equal to 0, shows us that we have a factor of p minus 1. So p of r can be alternatively written as r minus 1 times something, some second order polynomial. Doing the polynomial long division, which we'll skip just for the sake of brevity, that will be r squared minus 4r plus 13. One can now apply the quadratic formula as soon as you have a quadratic. That will give you a pair of roots. And of course, we noted that 1 was a root to begin with. Anytime we have a real root, that gives us a solution term of the form e to the root times x, but this is just a root of 1, so it's just 1 times x. Then, whenever we have a pair of complex conjugates, that now introduces trig terms. There are two parts to any complex number. There's a real part and an imaginary part. The real part is going to be the part that, just like a real number or a real root, that gives us an exponential term, this real part will also give us an exponential term. But that's not all. Because there is a imaginary part, the part that's paired with I, we also get trig factors here. Those factors will be cosine and sine of this imaginary coefficient times x. Now, which one goes with which? Should it be sine first or cosine? It's completely irrelevant. It's not like this root corresponds to this cosine or this root corresponds to this cosine. They're always coming in pairs here. Now, if we assemble all this, we can get a solution formula. And like we've seen in the past, we do have a singular solution of y is equal to 0. Let's look at our last example. Now, here we have a
sixth order
linear, constant coefficient, homogeneous differential equation. And I've pre-written the characteristic polynomial, which we know exactly how that's going to look at this point. And I've pre-found the roots. Now let's see what the solution terms will look like. In the case of a real number that has multiplicity greater than 1, we know what's going to happen there. We're going to have e to that real number times x. And then because of the multiplicity 2, we'll have this polynomial that is c1 plus c2, that is c0 plus c1x. Notice I was using c1, c2 before I started at 1 instead of 0, but it doesn't matter. I just like this a little better because it's x to the first degree, so it's c1. This is like x to the 0 degree, and so on, but it's irrelevant as long as they're different. Then in the case of the complex pair, we know that that will give us a pair of trig terms that are multiplied by an exponential. Now, in a similar way to what we saw with the exponential matching up with the real number, we're going to see the same thing here, where we multiply by polynomials. Because it's multiplicity 2, that gives us a polynomial with 2 degrees, a polynomial with 2 terms. Now notice I'm going to use different constants for the different trig terms. So I use a c2, c3 for the cosine, and then a c4 plus c5 for the sine. Now we assemble these all together to get the solution formula. I hope you found this video helpful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.